Definition rules for probability revolve around one essential idea, whether or not two events are mutually exclusive. Mutually exclusive means that two events cannot occur at the same time. So if they're not mutually exclusive, that event could be members of more than one category. We'll use our deck of cards as an example. In one of our previous questions, it asked us to find the probability of a 3 or a diamond. Well, it's possible in a deck of cards to have a card that meets both criteria. It could be a 3 and it could be a diamond. Okay, so those two events are not mutually exclusive. Whereas we can find the probability of a card being a 3 or that card being a 6. In this case, a card's not going to be a 3 and a 6 at the same time. It's either one or the other. So these two events are mutually exclusive. Okay, mutually exclusive means they can't occur at the same time. Not mutually exclusive means they can occur at the same time. So a card can be a 3 and a diamond, hence the 3 of diamonds. Okay, so that's a brief explanation there of what mutually exclusive events. So one more time, mutually exclusive events are two events that cannot occur at the same time. We've already talked about the complement. That's simply our 1 minus our regular probability. But the addition rules are stated right here. If the two events are mutually exclusive, such as the probability of our 3 or our 6, we simply add the probability of a 3 plus the probability of a 6 together, or A plus B. Probability of a 3 is 4 out of 52. A 6 is 4 out of 52. So we get 8 out of 52, and we simplify that down to be 2/13. Okay? If two events are not mutually exclusive, we still add their two probabilities together, but we subtract out the probability of being A and B, or what I would term that to be an overlap, or the events that can occur at the same time. So let's go back to our probability of a 3 or a diamond. The probability of a 3 plus the probability of a diamond minus the probability, in this case of the 3 of diamonds. There are 4 3s in a deck of cards. There are 13 diamonds, but there is one card that is the 3 of diamonds. So the 3 of diamonds has been added in here. It's been added in here. The card only occurs once, not twice. So I subtract out the second time we added it in, and we get 16 out of 52, or 4/13. Okay, so there's our brief explanation of our rules 1 and 2, mutually exclusive and not mutually exclusive. So as we look at a problem, we have to decide whether those two events are mutually exclusive or not mutually exclusive. So here, company has 66 employees. If one is chosen at random, what is the probability that a maintenance or a production worker is chosen? Let's start out. We have 51, 59. We have 66 total employees here. Now, based on this, they're broken into 4 different categories, and we don't have an employee that overlaps into each one, so these two events would be mutually exclusive. So we take the probability of a maintenance or a production worker and find the probability of a maintenance plus the probability of production. In this case, that would be 14 out of 66 plus 37 out of 66, which is 51 out of 66, and that would simplify to be 17/22. Okay, two events that are mutually exclusive. We're not going to be a maintenance and a production worker. We're going to fit in one department or another. Much like this next one, there are members of 4 political parties at a rally: 67 Democrats, 13 Republicans, 17 Independents, and 12 from the American Party. Find the probability of picking one to interview and getting either an independent or a member of the American Party. Okay, so the probability of independent or American Party, again, we're not going to have, based on how the information is presented especially, but we don't have members that are, or people that are members of 2 different parties. They're members of one or the other. So this would be a mutually exclusive event. So probability of independent plus the probability of American. So the probability of independent, there are 17 independents, a total of 80, 97, 109. There are 12 from the American Party. Oops, let's try that again. And we add those together and get 29 out of 109. Okay, so two quick examples of events that are mutually exclusive. We're not going to be members of both criteria here or all four criteria down here. Anything the same, it's going to be all separate. Oh, let's go back up here to the top. 36 people apply for a job, 20 men and 16 women. 8 of the men and 12 of the women have a PhD. If one person is selected at random for an interview, find the probability that the one chosen is a woman or has a PhD. So in this case, as we read through here, is it possible for a woman to have a PhD? It is, so these are not mutually exclusive. Okay, people can fit into both categories of being a woman or having a PhD, one or the other. So I'm going to write this out long version. Probability of a woman or having a PhD is the probability of selecting a woman plus the probability of selecting someone who has a PhD minus the probability that they fit into, I'll say, both categories, a woman and a PhD. So from our example, we have 36 total people. 16 of those are women, so 16 out of 36. Of those 36 people, 8 men and 12 women, or 20, have a PhD. So probably selecting someone who has a PhD is 20 out of 36. But we have 12 women that have PhDs, so those 12 women fit in here and in here. So we have to subtract those out, and that gives us 24 out of 36, or 2/3. Okay, so there's our first look at events that are not mutually exclusive, much like our card example in the last section. Another time here, party, there are 32 men, 16 of whom are without dates, 28 women, 12 of whom are without dates. Find the probability of picking someone at random and getting a person who is a woman or without a date. So again, notice that we can have women that don't have dates, so these two events are not mutually exclusive. So we'll write that out again. Probability of a woman or not having a date is the probability of selecting a woman plus the probability that person doesn't have a date minus the probability, and I'm going to continue with the phrase or word both, they fit into both categories. So it looks like there are 32 men and 28 women, or 60 total people at the party. Of those, 28 are women. There are a total of 16 and 12, or 28 people that don't have dates. So notice the dates is a separate category. People without dates, 16 men and 12 women don't have dates. And we subtract out that overlap of 12 women who don't have dates. So again, those 12 women were added to women, added to no dates, so we have to subtract those out. And we get 44 out of 60, and that would simplify then to be 11/15. Again, noting that our fractions are always put in simplest form. A couple more examples here. 47% of people read the newspaper every day, 62% of people watch the television news, and 25% do both. Find the probability of picking a person at random and getting someone who reads the newspaper or watches the television news. So the first question we have to ask ourselves, is it possible for someone to read the newspaper and also watch the television news? I would hope we'd all agree that a person could do both of those events in any given day. So those two events are not mutually exclusive, which means I'll write it out longhand first. So probability of reading the newspaper or watching TV, watching the television news, is the probability of reading the newspaper plus the probability of watching the television news minus the probability that they do both of those items. Okay, so a person can do one or the other. They don't have to necessarily read the newspaper. They could just watch the news on television, or they could read the newspaper and not watch TV, or obviously they could do both. So our probability of reading the newspaper is 47. Our probability of watching the television news is 62%. And those that do both, that fit into both categories, so 25% were added in here and here. We subtract that out. And if we do that, we get 84.84, or 84% do one or the other. So pretty much everybody is doing one or the other. One more time with that idea in mind. 38% of the people eat out once a week, 42% take home prepared food once a week, and 29% do both. Find the probability of selecting someone who eats out or takes home. Same general idea. They can eat out, they can take home, or they can do both in any given week. So we have not mutually exclusive events. So the probability of eating out or taking home is the probability of eating out plus the probability of taking home minus the probability that they do both of those things in any given week. Probability of eating out is 38%. The probability of taking home food once a week is 42%, and the probability of doing both is 29%. If we do the math there, then we should get 51.51 or 51% take home prepared food or eat out once a week, one or the other. And that gets us through our 2 addition rules.